And now, our final speaker, what I would like to say before his presentation, that's talking about different AutoML solutions. Authors use different solutions, and original ideas and approaches is really important for solving the tasks of deep machine learning. And this is what our final presentation by Nikolay Nikitin will be about open source evolutionary AutoML called FEDOT.
Good evening. I'm Nikitin Nikitin, and I had Intellectual Development Center in ITMO University, and I would like to talk about our development AutoML framework FEDOT. To begin with, a couple of words about what this framework is about, why we decided to develop it, and what makes it different from multiple AutoML solutions that exist and very often work pretty well. So the main focus of ours was on automated design of ML pipelines, not only with graph-based structure. So we abandoned simple search of pipeline solutions, and with the help of evolutionary algorithms, we solved the task of optimizing the structure of this graph and separately tuning hyperparameters using hyperopt. And this type of model was supposed to solve a pretty wide range of tasks, including classification, regression, and forecasting, predicting temporal rows, and images of temporal rows. So here we focus on maximal modularity and expansion and openness of the solution. Therefore, we have a lot of examples of adapting this approach to various tasks, including directly and indirectly connected with machine learning. We also tried to provide for maximum accessibility of the solution to the users. That's why there is an external lightweight interface, and there is a more advanced interface that is more cumbersome in terms of code strings, but it can help to configure the type of task solved, constraints on the structure, all hyperparameters of optimizer, and optimizer can be replaced as a whole. And the solution is accessible through GitHub and pipeline. As for the main ideas, why do we use this approach that initially looks a little bit more cumbersome than possible? So here we proceeded from a popular recent concept of composite AI. In many subject areas, there is a wide pool of existing foundation of different models based on physical equations. There are best practices on building models on data sets, and a particular thing here that is important for subject areas where this foundation is large, because the modeling task has been solved for them for dozens of years, like the sign on Earth and hydrometeorology. There, this basis is really huge. But recently, they also try to solve the same task with machine learning, and we can say that it is sometimes successful. So our task was to converge these two worlds of models, machine learning and classical subject areas, and on the other hand, maximally optimize their creation, because the volume of routine building this hybrid model is really huge. And there is also a problem here that experts in subject matters usually do not know much of machine learning, and vice versa. So that was a very interesting niche for, we can say, composite approach. How we try to implement it in practice. So we had a notion of composite pipelines, which is a heterogeneous graph structure that will consist of forecasted model operations on data. In the simplest way, that is ensemble or linear model, and in the more difficult way, the structure can consist of different types of models, different data sources, different connections. The most important thing is not to have cycles, and interactions can be different. That would allow to use this solution for various interesting tasks. Talking about the main functions, for example, the task of tuning parameters of pipeline was really interesting, unexpectedly interesting, and to set the parameters in expanded area is pretty well used. But when we have a heterograph structure with big data and various operations, working with this as with a black box can be done differently. And we implemented a strategy of tuning hyperparameters that is based on Bayesian optimization, and it can allow pretty efficiently setting hyperparameters. Post-setting of hyperparameters is not enough, and within evolution algorithm we also work on both structure and hyperpipe, and we focus on universality. That's why within one pipeline we can solve several tasks. So, for example, to adjust scores of classifier, we can use regression models with a value of probability adjusted to increase the quality. And we can also solve multimodal tasks where data sets consist of several subsets, for example, images, text, and tables. In this case, one composite model can solve the modeling task using all these data sources, bearing in mind its heterogeneous structure. Another important aspect is that it would be good to explain these pipelines to the user so that they can understand what each block is needed. Therefore, we carried out sensitivity analysis. And the last section, as the models are pretty complicated, on the one hand, we had maximally convenient expert in virtue of JSON, and on the other hand, the import of the same sort structured. And the user, on the other hand, can create a lightweight pipeline using their knowledge to use it as initial approximation for optimizer. So to proceed from not random options, but from what user has put forward, and then already optimize and simplify this offer. We have come up with pretty large-scale evolutionary optimizer that has pretty many particular features that are not very frequently found in AutoML. First of all, its ability to self-tune, so that you should not set the population size and all other things that we need to set for AutoMLs based on genetics. So we came up with a parameter-free approach that depends on the convergence dynamics, either increases population size or changes the rotation variance and so on and so forth. We also have evolutionary operators broken down in two groups, common ones and task-specific for ML. Like mutation of hyperparameters and so on. Why does it make sense to break it down into two groups? Because optimizer can be used not only for ML models. For example, if you have only general mutations for graphs, we can use the same optimizer for identification of networks, several networks, and we were pretty successful. We are now trying to apply it to identify differential equations, and it is pretty successful as well. As I have said, the main operation is mutation and crossover, and here are examples of several options of mutations used here, and one of crossover options. In graphs, even without additional transformations of genotype, it is possible to implement these operations that allow to give birth to new pipelines out of the existing ones. Naturally, very frequently, the user wants to take into consideration not only a single criterion to identify the pipeline. On the one hand, it can be several metrics of the quality, model quality at test sampling, but on the other hand, it can be also additional requirements, for example, the complexity of the model. And here we can see an example of how we found several options of a pipeline, from simplest, non-efficient, and more complex, but more efficient. And very interestingly, our optimizer supports various options of tasks or setting these metrics. For example, you can use not complexity, but robustness. And there are effective models of data that are not so sustainable to noise, and others that are. And optimizer can be used to solve different tasks. And in many subject areas, there are their own target functions that we would be happy to use. And here, in addition to the standard ones, we can set our own functions, various that will be used. On the right-hand side, you can see the result of adding regularization operator that allows to avoid overcomplication. And we can use subgraphs out of each graph, and then simplification of graph will not lead to loss of quality in one of the metrics. And the simplified representation can be used instead of stops. And this logic has given us growth in quantity. Apart from regression implementation, we also have time series forecasting. As it is, how it is implemented here, the block of transformation into regular matrix is the key. And on the one hand, it is pretty easy, and it is not us who invented that, but the existence of graph pipelines enables to build an ensemble structure. For example, there can be several transformations with several window sizes, and there can be different options of regression models for each of the tables received, and there can be operation of downsizing the long series of windows, and additionally multi-dimensional, single-dimensional series are supported. And apart from that, to increase the quality of this automatic model building, we used an additional block that allows to work with multi-scale time series. Well, actually, the idea is close to boosting, but not at the level of pipeline, but at the level of model. We have model A, and we add model B to it that tries to compensate the prediction error of model A, and then they are united into an ensemble. And the task was to increase the quality, but for time series it is of particular interest because it enables us to work with multi-dimensional processes. So model A is responsible for one dimension, model B is responsible for another dimension, and you can add random number of cascades, and it will work pretty efficiently sometimes. And to optimize it so that these cascades can be added by the optimizer, we added mutation operation that adds this cascade and carried out the support of all types of tasks that are solved with this help. We have also implemented multimodality. Now we have a prototype that allows to work with texts and images and tabular data within one model. You can see an example for MDB database that has textual descriptions of movies and advertisement of movements, and the tables are modulated with random and there is a separate mini pipeline for scenarios. An optimizer can build this model, and if one of these data modality is excessive, it will just get rid of it and simplify the pipeline. If only tabular signs, tabular features are enough, only they will stay. If not, all the modalities will be used, and their mutual influence will be taken into consideration. I have mentioned sensitivity analysis as well. The point is that we try to test and delete every feature in the pipeline to understand what influence it has. And it allows us to simplify pipelines, getting rid of the blocks that do not give a significant growth. And on the other hand, it gives explainability, showing the input, the contribution of the result of modeling into each of the blocks. And within the project, with our colleagues from Huawei, we have a future research that will try to optimize graph structure with sensitivity analysis. So that is like making AutoML more controlled and minimizing the random part of selection and maximally using the information on the effect that each of the blocks contributes, like which effect of which cluster of data is in charge of what and what scale of the process we can reproduce better with this or that block. Therefore, the user will be able to receive more information about structure, and we will be able to get a better result in less time. To additionally enhance visualization, we also implemented a prototype of Z interface that allows to solve several tasks. So that is interactive editing of any pipeline. The user here can themselves introduce their own editing and launch the AutoML, and they can analyze the history to see what particular pipeline was received through which way, which operators got part in it, and there is this detailed visualization of the evolution history. And it is an open source product that can be unrolled locally or can be seen now open source. GitHub. As I have said, we tried to come up with a maximally simple interface, which is user-friendly. You just need to indicate the problem, the time out, and data array, and the target feature, and the classification task will be solved. The same is true for series forecasting, but you also need to indicate the forecast depth. At the stage of forecasting, the forecast can be of any length, but the optimization will be done for the set one. And you can manually get the pipeline together. The user will set primary and secondary nodes of graphs, assemble the pipeline, and it can be sent to optimizer. And there is initial approximation, baseline, and so on, which is pretty convenient in many cases. Now let us have a look at some benchmarking and applications for real tasks. Here are some results from one of our articles on one of regression datasets. We compared with TPOT, MLBox, and XGBoost. Here you just, we did it just to show that the approach works, and it works on the same genetics as the TPOTs, and it wins over linear pipelines, easy options. And as for benchmarking, we used it here, and we came up with our own benchmarking for strings, that is economic data and thread, TP are turbulent data, and power stations, and smart are smart sensors. And we did it better. We compared time series of different lengths, and we had different kind of forecasts, and at the bottom you can see that profit gives non-realistic forecast. AutoTS does not always forecast per period, and we are planning to test it wider. And as for tabular data, we are planning to launch the framework on the open data science benchmark that we heard about recently. That is a very interesting development. We have added our baseline but have not launched it yet. I hope we will do it in the near future to see what comes out of it. Talking about an example on real data, I would like to give you one example. We took part in hackathon with a task to forecast the flooding on the Lena River, and we have a lot of time series of atmospheric measurements, measurements of the river level at hydro posts, and interestingly, we just simply took the data and sent evolution optimizer FEDOT, set the parameters, and the result that we received from the very beginning was better than all other participants. So the forecasting approach to forecast the series performed really well. On the other hand, we added an applied model based on equations from hydrology, which enabled us to enhance the quality of forecasting even more. So this focus on heterogeneous models proved really useful and successful. Talking about our future plans of further development of this tool, we are planning to expand new tasks like implementing support to time series classification, to improve multimodality, to show more interesting examples, to integrate with existing tools from MLOps, to be able to use it in production, and also to enhance controllability and interpretability. The framework is fully open. Here you can see a link to GitHub and to some other resources of ours in Telegram channel, and there is a short YouTube video that shows approximately what I have been talking about, and a link to our article, journal article, where we give details on how it is all arranged inside. And we are open to any contribution. We would be happy for and thankful for stars. So that is briefly what we have. Thank you very much for your attention. I will be happy to entertain your questions. Thank you, Nikolay. What I would like to ask you, we heard a lot about deep learning, GPU, and so on. And what can you say about GPU at your side and cloud sources?
On the one hand, work with images as part of multimodality. We use solutions from Keras, and there you can use GPU. And the classical models of GPU with rapids, QDF, and others. If the optimizer will be asked to work in GPU mode, it will be able to implement a number of models in boosting mode for GPU, and part of the pipeline will be implemented on processors and others on the graphic cards. And it really accelerates the process if there is access to it. And training pipeline for the fitness, if it's remote, it's helpful if you use RES. Now it's only used for DataML, calculation platform developed by ITMO Institute, so it can be implemented seamlessly, adding resources of the customer. So yes, it supports it. The answer is okay. And another question: not just people that work with ML. There was a question that is possible to build models not related to ML, but you need to adapt the evolution kernel. What's required from the user to achieve this result? From the user, you need the construction blocks he wants to use to build the models, operators of mutations he believes correct, how to calculate the target function, and that's it. And then the optimizer uses the abstractions of a nodes graph, and where you have links between the nodes. And it doesn't really matter what the end user will transform this model into. He implements that functions, and then the reverse process, and then the entire logic of evolution can be used. Well, it sounds really cool, like a construction game for pipelines, for models which are not in ML.
Ну и, собственно, мы, конечно же, ждем вас
And of course, we await your solution in ODS benchmark. It would be interesting to check whether it's applicable for some data sets. What is the result? What's the outcome? Of course, it would be interesting to try. One thing we should be concerned about, but when you expand the search space, you need more time to achieve a result. So, and if you are pressed for time, then, well, it depends on the search horizon to find something efficient. Okay, yes, it's a standard story, and in the benchmark itself, there will be different events, so let's check what can be calculated when you have much time, or you can calculate something in 30 seconds in a data set, so you'll have a lot of room for creativity here. So I hope we will find points of contact.
Okay.
Okay. Thanks, Nikolay.